All right, let's get started. Um, my name is Kevin. I'm filling in for Matt. I work with Matt at his company, and he's out of town for the week, so I should be back on Monday, I believe. Just a note about the final project. Late days cannot be used for the final project, just so you know. All right. So I believe you guys talked a little bit about OpenGL last week. How do you guys feel about OpenGL? You understand, conceptually at least? Hopefully hopefully it makes sense. But we'll review a bit about it today. So this is the slide about OpenGL. This is the components that you need for an OpenGL application. So the top three, the UI window, the GLK view controller, the GLK view, those are just the setup pieces provided by Apple. So you have some setup code additionally with that to build up, to pass in the additional parameters. But the components you care about primarily are the vertex shader, the fragment shader, and the OpenGL program. And you're passing in your attribute arrays and any uniform values. Great. You guys understand the difference between. Do you guys know what a vertex is? Vertex? Is that clear? So vertex represents one component of your geometry. So in the example of a triangle is composed of 3 points. 3 points represent the vertex, but it's not just those 3 points. It can be additional information. You can associate additional information with each of those points. Oftentimes, it's a normal value indicating which direction the triangle is. But it's more of or the position in your geometry of out, orthogonal to your plane. It is your tangential plane, as it were. So you often have a normal value. You often have a color sometimes, or a texture coordinate. So there's additional information that's bundled together and we call the vertex. We also have the fragment. Fragment, at its core, it's oftentimes we can think of it as a pixel. An individual pixel is a fragment. It's not truly the case. Oftentimes, an individual pixel on screen is represented by multiple fragments. Fragment just is a component, a small component that is used to be drawn. And oftentimes, an individual pixel is composed of multiple renderings of a single fragment. So that's the basic component of the vertex shader and the fragment shader. Those are strings, simple strings, files. You pass into your program, pass it in as a string, and you pass it to OpenGL, and OpenGL will compile it down to a binary, and that binary is shipped off to the GPU. So the GPU then will do all the work of distributing it. OpenGL will make sure it's all distributed correctly, and it goes through that pipeline, and it ends up on screen. So that's the basic flow. Oh, here it is. Perfect. So this is the OpenGL ES pipeline. We have passing some data, and that goes into some primitive processing. It converts that into OpenGL, the coordinate space for OpenGL. And we pass that to our vertex shader. The vertex shader then is the component that you write, that you will operate on, transforming your coordinates, transforming your normals, whatever you want to do. You have that control. You have that injection point. That's passed off the rasterizer, which will flatten it down into what is actually on screen, or what will be on screen, most likely. It is possible that some of this information is thrown out. Anyway, this information then gets passed to the fragment shader. The fragment shader then operates on that, and its output is a color. The color of the pixel that it represents. And that gets passed to the fragment processing, which will combine all those fragments, sometimes just a single fragment, sometimes multiple fragments, into the actual pixel, and that gets written out to the frame buffer. Frame buffer is then refreshed on screen. So the components that we're concerned about are the input data, the scene data or OBJ files. OBJ files are just 3D models, very simple 3D models. The vertex shader is the component that we're going to write, and the fragment shader. So those are the three components that we were dealing with. So this is a very basic program and shaders. So this very first one is using a program, find, passing in some floats, and drawing them. In the middle here we have a vertex shader. And all this shader does is pass through the position, convert the 2D position to a 4D position, just filling in the values that don't exist. And the fragment shader just presents a color, simple color. This is green with 100% alpha, or 100% opaque. Simple shader, very simple. Here's a slightly more complicated shader, passing in some uniforms, but the core of it is the idea that we could pass in attributes and uniforms. Attributes are for every single vertex. So you pass in arrays. Every single vertex shader, when the vertex shader, it operates on a unique attribute. This position, for example, is unique to every instance, depending on which you pass in. The uniform, this uniform vec2, this is the same for every single run of that shader. So if you pass in a big model, say this bunny, Stanford bunny, if you pass in all the geometry for that, hundreds of thousands of points, maybe tens of thousands of points, I don't know how many triangles it has, but you pass that in, that is all passed to the position vertex, or position vector. It's probably be a vec3 in this case, because it's a 3D model, or a vec4. But that, if you want to move around on screen, you can move around your source data, or you can just pass it a translation, and it affects the entire model because it's applied the same for every single vertex. Right? Barycentric coordinates are just a way of defining a position within your triangle. It's not entirely relevant for today, but it's good to be aware of. The concept of it is you have these 3 lambda values, and they're associated with each of these points, and they add up to 1. So this is the formula. I like to think of it as a kind of a percentage-based thing. So you have lambda 1 associated with A. It's like 30% of A. This makes a lot of sense if you have some colors. So another image here. Matt knows a lot more about this, and he can explain it better. I'll probably have him explain it more when he gets here, when he is back. But the idea of this point P is defined with some component of that blue, some component of that red, some component of that green, depending on its position. Yeah, so that's basically it. These barycentric coordinates are able to define every single point within this triangle, including the vertices themselves and the edges. Kind of cool. It's how we do things like texturing. It just makes use of these barycentric coordinates. Yep. Again, Matt will talk about that more, I hope. I don't understand his slides entirely. But today we'll be focusing on primarily the setup of this whole flow, the vertex shader, the fragment shader, and the program, the OpenGL program, as well as learning how to interact with writing your own vertex shader and why that's valuable. All right, any questions so far? OpenGL makes sense so far? All right, let's dig into it a bit. So this should be this is the web map. This is the first lecture. All right. This is where we left off last time. We defined a sprite view controller, and a sprite view controller is a subclass of GLK view controller. All right, he left off at the same spot. So he, all he did was define the GLK context, load the shader as a string, load the path of the shader from the bundle, load the shader as a string, and print it out. So this should be, also he's clearing the color to green. I believe this is identical to lecture 1. The only difference is he named his vertex rather than vertex sprite vertex. I'm just going to use lecture 1 for now. All right. So if I run this, the only thing I'm doing is I'm clearing the color, specifying the clear color to be green, and I call clear. So I've got a green screen. Not that useful. So I'm going to first go through some of the setup code to set up that vertex shader, that fragment shader, and build and link that program. Okay. So again, OpenGL is a C library, and we are not in C, nor are we in a C superset language, subset language, whichever one it is. Essentially, we can't call the C functions the same way. So there are some weird little interactions dealing with that C interface. But most of that's in the setup of the shaders. A bit tough to deal with, but we'll get through it. So first thing, we printed out the source of that shader. Let me take a look at this. Okay, so in order to build the shader, we need to create the shader first. So create the shader, and there's a method called GL_create_shader, conveniently enough, and it returns a type GLUint. So we have a uint. Type is the type of shader that we want to create. I can go look up this method, GL_create_shader, and GL_create_shader. Create shader. The type can be either a vertex shader or a fragment shader. So we want to do a vertex shader, GL_vertex_shader. So GL_vertex_shader. And it complains because it cannot convert type 832 to GLUnum. This is one of those things that this will work perfectly fine in C, but because we're in Swift and our type safety system will complain at us, we need to wrap this as a GLUnum. Right? So we have our vertex shader, created it, it's just an integer. We just reference it by an integer that the OpenGL system creates. Great, so we have a shader, we need to compile the shader. Easy enough. GL shader compile. GL compile shader. We pass it the same vertex shader. All right. So we've compiled the shader, but we're not doing anything with it. It doesn't mean anything. We've never passed it our source code. So we need to add our source code. GL shader source. This takes 4 parameters, the shader, which we just pass in the vertex shader that we created. The count, which is 1. String. String is an unsafe pointer to an unsafe pointer to GL char. So essentially char star star in C. So an array of strings. When we build our shaders, we can actually upload more than one source file, more than one string if we want to. Not entirely sure why we would want to do that, but if you've got a complicated shader, maybe it's valuable to you. We don't need to do that, so we're just going to upload one shader. Length is the array of, it's an unsafe pointer to GL int. So it's the array of those length of strings, because C strings don't have length. You have to call strlen to get the length of the strings. We don't have to pass it in for some reason. Matt understands better. I think it's just how their wrapper library works that we don't actually have to pass in those strings. But we just pass in the array of that data. The raw byte data, string data, as a char star. So to do that, we have our source, and we can get the data as a string. But really, we already had the data. We never needed to convert it to a string. So we can create a data object from file. Sure. From file, and it takes a URL. So instead of bundle.main, instead of asking for the path, we can ask for the URL. URL with extension. And URL for resource vertex GLSL. Great. We never need the string as a. We never need the vertex shader source as a string unless we want to print it out. So I'm just going to take the raw data. So I get the data as a data object, and I can do. It's complaining because it's marked as throws. All right, so we have the data, but this is a foundation object or a Swift object. This is not the raw bytes. So there's now a pointer to bytes. So I should be able to pass this straight through. Never actually tested this, but it makes sense that it should work. All right, this was Terrible idea. It's going to undo all that. Conceptually, it makes sense. I'm passing in the same data. I never need it to convert it to a string, but dealing with Swift sometimes, it's a little tricky. Well, that was fun. Okay, do it a different way. We'll do it the way that I know works. All right, so we have the source as a string. We just need the byte data. Vertex, shader, data. And this is, I don't know what type it is yet. Vertex, shader source. But I want the C string using the UTF-8 encoding. So this is now type unsafe pointer uint8 optional. And this takes an unsafe pointer to glchar. Glchar is type def to char. Oh. But it should be, okay, it's alias to int8. It's defined as int8. So this vertex data, which is pointer to int8, it's the same as this glchar. So I can just pass that here. And I pass the pointer, because it's a pointer pointers, and I just have one pointer. So I pass it with the ampersand. And I need to change this to a var, because it could be changed. So dealing with these C APIs, it's a bit burdensome, but you kind of have to deal with it if you want to deal with some of the C APIs. A lot of libraries will provide a C front end for you, and oftentimes you'll either have to download a wrapper or write a wrapper yourself, or deal with something like this, a bit more complicated. All right, so we have our shader, we have the data, create the shader, upload the source, compile. Perfect, you've compiled the shader. But what happens if it fails? I look at GL compile shader and there's no return at all. So I need to ask the shader for its status. OpenGL is a state machine, so a lot of these things will be like this. You'll have to ask for some of this information. So that's simple enough in theory. GL shader. GL get shader IV. GL get shader IV is return a parameter from a shader object. Shader, you pass in the shader, you pass in the p name, which is the object parameter, and accepts shader type, delete status, compile status, info log, shader length. Compile status sounds exactly like what we want. So you pass in the vertex shader, the parameter name, it's a GL enum, so to wrap it again. And it was shader compile status, GL compile status. And this asks for an unsafe mutable pointer. So this is a out parameter. If you've dealt with C# or anything like that, you've seen out parameters. Or in C, you pass in a pointer, and then that function will set the value for you. And that's what this is. So it takes in unsafe mutable pointer to a GL int. So we need to find a GL int, and we'll call it compile status, vertex, compile status. I'm going to initialize it as false, and pass it the pointer value for my variable. So I can just check that compile status now. If the compile status is false, then print out a message. Otherwise, if it succeeds, we got a different message. Great. There's one more thing. This context also needs to be set as the shared context. Or the current context. And I can just pass in the context that I created. Oops. All right. So hopefully compilation will succeed. If not, I should get a message to know whether it succeeded or not, which is very valuable. A lot of times dealing with OpenGL, it's hard to debug, so this is kind of what you get. Because you're dealing with a GPU, and debugging the GPU with hundreds of cores is very difficult. It's hard to set a breakpoint. So a lot of it is just trial and error, unfortunately. But okay, we get compilation failed, which is not encouraging. If I look at the shader, seems reasonable, but I noticed that it's missing the semicolon. Semicolon is required. I'll run it again. Hey, it compiled successfully. But if I go back to this, main GL position vec4, it seems valid, but it's hard to figure out why. So I'd like a little bit more information. I can get a log of the compilation, and to do so, I again need to ask the shader for the log. So I need to do the same thing here, calling shader get IV. I'm going to check the documentation one more time. So GL shader get IV accepts shader type, not useful, delete status, compile status, info log length, and source length. So I can get the length of the log. So in the same way as getting the compile status, I define the integer, and I call GL get shader IV, pass in the shader, parameter name, pass in the length, and I pass the same pointer to my output. Great. But I actually want to get the information out. And so there's a method called GL shader info log. Pass the shader again. Buffer size. Well, the size of the buffer is just how long the log is, so I can pass the log length. Length, I'm not sure what that is. You pass it nil, and Matt will tell you why that is nil. And info log is the out parameter. So I need to find an unsafe mutable pointer to a GL char buffer. Great. So I'm going to define a buffer. Unsafe mutable pointer, type GL char. And I want to allocate as many bytes as are in the log. So I define that capacity, and I can pass in that buffer to my method call. And here it complains that glint is not int 32. So in C, this would work perfectly fine. It would do that cast for you. It would just treat it as a glint. But here, I need to specify that it is an int, not a glint. Great. So now I have this buffer. The buffer is now filled with all the string data of my log. So I can turn that buffer into a string. String. It is string with C string. Pass in the C string of log buffer. And then just print it out. Right, compilation failed. Error. 0, line 3, bracket, syntax error, syntax error. Not that useful, but at the very least we get a line number. And a line number is reasonably helpful. So line 3, I can say, oh, line 3, before that, syntax error, semicolon. Semicolon is what I need. Perfect. Run it again. And it should succeed. Compiled successfully. Beautiful. So a bunch of boilerplate code just to load the vertex shader. Luckily, the fragment shader is the exact same process. So I'm going to just fatal error. Here. So if the shader doesn't compile, our program doesn't execute at all. And for the fragment shader, I can just copy paste all that code and just replace all the vertices with the vertex definitions with fragment. Alright, so the only thing that really changed, the biggest thing that changed, was the fact when you create the fragment shader, you create it as a fragment shader, not as a vertex shader. So I believe they should also error out because there's no semicolon in the fragment shader, that is. And indeed, fragment shader failed, line 74, because of line 3 in the fragment shader, which has no semicolon, or the line before has no semicolon. Perfect. Great, so now my shader is compiled, my program is still running, and I still have a green screen. I need to combine these shaders and link them into a program. I go back to the slides. We have the vertex shader, we've written it, we've compiled it, done the same thing with the fragment shader, compiled it. We just need to combine them into the program. The program is what we pass to the GPU, or OpenGL in the GPU. It passes it onto the GPU. Essentially, the program is what the GPU runs. So to do that, It's quite simple. Call create program. Aptly named method. With the program, we just attach our shaders. Vertex shader. And the fragment shader. And then we call link. Link the program together. But it's possible for a program not to link. It is possible to error out, just like our fragment shaders failing. This usually happens when your fragment shader doesn't compile, or you only pass it one of the shaders. So the shaders, the program needs one vertex shader, exactly one vertex shader, exactly one fragment shader. So we can check it in very much the same way as we did with our compiling errors for our shaders. Program. GL get program IV, just like GL get shader IV. Pass it a program. Pass it a name. Pass it an out parameter. I can go check the documentation one more time. And it accepts more parameters, but the one we want is probably GL link status. No, returns true if the last link operation on program was successful. Great. So I want to get the link status, and I need an out parameter. Default to false. And check that link status again. And just the same way, I can get the log and print it out. So I can copy paste this. The only difference is instead of asking it from the shader, I need to ask it from the program. And instead of GL get shader log, it should be get program log, program info log. Great. So if I don't have any shaders attached at all, linking should fail. Great. Linking program failed. OpenGL ES requires exactly one vertex and one fragment shader to validly link. So make sure it does link properly. Great. We got a green screen again. So that was a lot of work to get really nowhere. But we have our pipeline full. We're building our fragment shader, our vertex shader, compiling it. So all we need to do is send it the data and adjust our shaders as we need. Yes, question? Context, yes. So this is the line I added that was not here when Matt gave me the data, the application. Without this line, it doesn't know which context to use, so it seems like your programs will always fail to link, or always fail to, your shaders will always fail to compile, and they'll usually not have a log. That was my experience. So great. So we have our shaders. We have our fragments. We have both our shaders. We have our program. Last step is to actually use the program. If we don't use the program, it never gets uploaded to the GPU, I think. Pretty sure. And it doesn't know what to do, what shaders to run. You can also swap out shaders or programs if you want to. So if you have some vertex shader, you have some special fragment shader, but you only want it for one object, you can just swap out which program. It can be very useful. Great. Any questions so far? A lot of boilerplate code. Sorry, but that's the worst of it. Make sense? Conceptually, it's very simple. Compile the shader, check the logs. Compile the shader, check the logs. Link the program, check the logs. All right. So if you look at this, we have our vertex shader. It's very basic, but it works. We have our fragment shader, very basic, but it works. And we have a program that's linked with both those shaders, and we've enabled it. So we just need to pass it this data. We just need to pass it this data object from a scene or an OBJ file. We can just pass in raw data as we need though. All right. Let's do, the drawing is relatively simple. I think Matt showed you this very briefly, at least the method. There's a method called GLDrawArrays. There's a couple methods with GLDraw. Draw buffers, draw text, draw elements, all sorts of stuff. GLDrawArrays is probably what you'll most likely use. All right. So if I take a look at GLDrawArrays documentation, takes the mode, which is the kind of primitive to render. Points, line strip, line loop, lines, triangle strip, triangle fan, and triangles. There's no neat little image. But we can just draw single points if we want to. It's not necessarily useful. You can draw triangles, which you pass in 3 vertices each. You can draw lines, or you can draw something like triangle strip. So triangle strip will reuse the last 2 vertices. So you just add one more vertex, and you add a new triangle. So in this example, 1, 2, 3, 4, 5, 6 vertices, and you get 4 triangles. You define the first 3, you add vertex 3, you get a free triangle based on those previous 2. Triangle fan is similar, but it just uses the very first point as, it always uses the first point. So this is a good image. So there's points, lines, you just pass it a single line. Lines, line strip will reuse the previous point for vertex. Line loop will close. GL quads and GL quad strip, I guess OpenGL does have quad support or polygon support, but OpenGL ES does not, I believe. But it's not terribly difficult. You can just compose your quads or your polygons of multiple triangles. All right, so let's start with triangle. Triangle is simple to understand. Specify 3 points. So, GL enum triangles. So we'll leave this for now. We need to pass in some actual data, some vertices. So we use GL vertex attrib pointer to do that. So we actually need some data that we want to send to the vertex shader or OpenGL. So let's define the triangle. Triangle as an array of floats. Makes sense. So triangle. Draw any triangle we want. Starting with 0, 0. Makes sense. but what do these other coordinates represent? It seems to me that you can define a triangle however you want. You just need to find 3 points, and as long as they don't form a line, it's a triangle. We can define it in 3D space. We can define it in 2D space. We can define it in 2D space for now, but if you wanted to, you can define in 3D space. But the bounds of the triangle, if we draw, depends on how big we draw it. It could be a single pixel, or it could be the entire screen, or more than the entire screen, which is not ideal. So OpenGL works from the bounds of OpenGL are -1 to 1, which is nice to know, but in the end, it doesn't really matter. You can pass it any vertices in any coordinate space you want. You just need to be sure to convert that into OpenGL coordinates at some point. You can do that here, or you can do that in your vertex shader. Let's just do it here for now. We'll define it in OpenGL coordinates so we get close to exactly what we want. So, rather, we can define it here so we don't have to do any additional conversion. We'll define it in OpenGL coordinate space. So I'll start at 0, 0. Start at 0. Do 1.0. All right. So this defines a triangle. Oh, good catch. So this defines a triangle. Yes, defines a triangle. So I just need to send that data to the OpenGL. And I do that with GL vertex attrib pointer. Let's skip index for now. Size is how many vertices compose your triangle, or each vertex. In this scenario, it's 2, but if we wanted a 3D triangle, we could change this to 3. 2 vertices per vertex. Two values per vertex. And the type of each value is we're passing in floats. So we tell it that we're passing in floats. Normalized is false for some reason. Don't remember why. Let's see if I can look it up. GL vertex attrib pointer. Oops. All right, normalized. Specify whether fixed data points should be normalized or converted directly as fixed values. Okay, so when they're normalized, the act of uploading it will normalize it in some way. I'm assuming based on the input data, to be sure that it's between 0 or -1 and 1. But we're doing that already, so there's no need to do that. Play around with that. Okay, so we pass in false stride. Stride is how many bytes to step over until the next vertex. So here, floats are 32 bits. So this is 8 bits each vertex. This should be 8. So you can, if you want to, you can add additional data. You could add normal data, you can add color data, you can add texture data, whatever you want, as long as your data is consistent in how far you jump between each vertex. It can be nice. It just often depends on how you get your source data. Sometimes people who create models will interlace. Sometimes they'll give it to you separately. It can be useful. And pointer is just the position of the array. Index, check the documentation of this one more time. It says specifies the index of the generic vertex attribute to be modified. So attributes are passed to the vertex shader. And they're passed as an attribute position. But we don't deal with it in that string position, the string position. We deal with it with this index. So we need to some way to link up this index that we define to the actual string pointer, so it knows the position in the shader. So this is just a number. We can use pretty much any number. But in order to actually create that linkage, we need to declare it. So we can call GL attrib, GL bind attrib location. So bind attrib location will create that linkage. So we pass it the program. We pass it the index that we want to bind. We pass it a pointer to GL char, or we can just pass it a string, and Swift will convert that to the correct GL char array, which is nice. So we're defining 0 as position. Great. So now we have a linkage between the position, the string position, and the integer 0. So when we now call vertex trib pointer index, we pass it 0, which corresponds to position. So now we are uploading the correct data, and it knows how to link that the data there. So when we draw arrays, draw takes in 3 parameters. First is the mode. We can draw lines, we can draw line strip, we can draw points, whatever we want. First is the index of the first vertex, which is 0, which seems kind of odd, but it can be useful sometimes to draw a subset of the array of data that you pass in. It's nice because you're not having to constantly upload more data. You can just have all the data, and you just have little peeks into it. It can be useful. Most of the time you will probably not have to deal with it, but it can be nice. Count is the number of vertices, not the number of triangles. So it's one triangle, and one triangle is composed of 3 vertices. So I can draw 3. Perfect. So just to recap, we've defined our data. We've defined it in a normalized way already. We've attributed it to the position array, of the position attribute that we still need to define in retrospect. We need to define it so we can link it to the actual position. I think this actually fails if I try to link without the attribute being there. Nope, apparently not. All right. Anyway, so we need to define our attribute. And it's a vec2 because we specified that our vertex has two values in it. And we call the position. So here, instead of vec4, we do position.x, position.y. We have no z value, and we're going to use 1.0 for w. Great. And if we look at our fragment shader, we expect this to be red 1, blue, green 1, blue 0. So this should be yellow. You should see a yellow triangle. And we see nothing. And we have no log. We can't debug it, which is really frustrating. A lot of this OpenGL stuff is a lot of boilerplate code, and if you miss one piece, you get nothing. Yeah, you just got to deal with it. There's not much you can do. A lot of times, it helps just to go as simple as you can and try to build up. In this case, a weird little quirk about OpenGL is that binding the attribute is not enough. You still need to enable it, which can be nice. You can. It's an optimization. You can disable vertices that you, or attributes that you don't need. I think, pretty sure. But it's annoying if you're first dealing with it. enable the vertex array, and great, we get our triangle. If we look at our triangle, I said that it goes from -1 to 1. So this is 0, 0. 1, 1, 0 is this one, and 1, 1 is this one on the top right. So OpenGL is Y points up, whereas core graphics, what we're used to with DrawRect, Y points down, which is something you have to deal with, just one of those quirks of OpenGL. All right, cool. We have a lot of boilerplate code, but we have draw triangle. And we can do this super simply with core graphics. So what's the point? Well, we're doing it on the GPU. With a simple scenario, core graphics would be probably suffice, but we're doing it on the GPU. We're offloading a lot of work to the GPU. And we can add additional, we can customize our shaders in such a way to do more interesting things. Let me do one more thing. I want to make a quad. Instead of a triangle, I'm going to fill in this top left portion as well. So I can copy paste this, and the only difference is this 1, 0, this bottom right needs to go to the top left. And instead of drawing 3 vertices, I draw 6 vertices. Beautiful. Got my quad, but I defined my quad with 6 points rather than 4, which is all that I need, in truth. So I can take out just the point that matters, and instead of drawing triangles, I draw a triangle strip. And instead of 6 vertices, I draw 4 vertices. And I think this may not work. The only issue with this is you need to be sure that you position your vertices in the correct order, and I believe it's not in the correct order. It is not. So it's drawing from 0 to bottom right to the top left, and then it's drawing just this segment. So we need to reorder our vertices. And that should do it. Beautiful. So I'm defining my geometry with less vertices, which is easier for me to maintain. Arguably. It still can be tricky depending on your ordering of your vertices. All right. I'm going to shrink this down slightly. And I want to move it around. I want to see, I'm calling this draw roughly 60 times a second, but I'm not getting any performance. I'm using that performance and I'm not seeing any real change. I can just draw it once. But if I want to do some animation with it, move around my quad, it's really simple. I just need to define a translation. And as I redraw, I can just update my translation. So I can change the geometry every single time and upload it every single time. And for this scenario, maybe it's okay, but if I have a very large, hundreds of thousands of vertices, it's overkill. It's a waste of performance. I can offload all of that computation. Even a simple add or a scale can be hugely more performant by pushing that load off to the GPU. So I can go in here, and every time I translate, I can add my offset. But it's work that I don't need to do. So this would work. But instead, I want to upload that data to the fragment shader. And again, we're using uniforms rather than attributes. Uniforms, again, are the same for all vertices when you draw, whereas attributes are unique. You have a different vertex. The shader works on a different vertex in your list of vertices. All right, so uniforms are relatively simple. You just define it. You just pass it uniforms. There's all these methods that you can pass in a uniform. We just want to pass in 2 floats. Yes, 2 floats. Translate x, translate y. Location, as it says, well, it's location of the program. Location of the program, so these names, no it's not, pardon me. You get the uniform location. You pass it a name. So I'm passing in a uniform of a 2-float uniform. So I need to find that uniform in my fragment shader, my vertex shader rather. So I can do attribute uniform, and I called it translate. So here, instead of position.x, I can add the translation. Add the translation. So this applies to every single uniform. So the geometry as a whole actually moves, rather than just one vertex. And I get the location of the uniform, and I called it translate. And I pass the program. And it errors because program is undefined. Because program was a local variable here. No problem. I just need to promote it to an instance variable. And should do it. Program. Program. Vertex shader failed. What do you do? Oh. Undefined identifier translate. Translate. So even the bare bones shader compilation logs can be useful. They're certainly better than a binary did compile, did not compile. Great. So now we're passing in our uniform value. We get some translation. I'm just going to go on and on forever. So in my application, I could probably do something smarter. Probably do something like time. Increment time. And I could pass in some sign value based on the time. Get it to bounce around more nicely. Do a lot of things like that. Yeah, I think that's about it. Any questions? Does this make sense? So, just recap briefly. Today we talked about turning our vertex shader string, loading it from file, compiling it, which is easy enough. Upload it to the, we set the source, compile it, check the logs, create a program, attach the shaders, link it. We bind the attributes. We bind them by name, by string name, giving it an ID that we use to reference that attribute. Link it, check the logs. And as we draw, all we are doing here is setting the data. In actuality, we only need to do this once, because it's a state machine. That information lies within the state machine. So we only need to truly link it once. So here we are uploading the data of the triangle. And rather than adjusting the geometry of the triangle, we just change the, we just upload the uniform. Uniform is consistent for every single vertex, whereas attributes are different for every vertex. So if we want another quad, well, it's quite easy. We just draw another quad. And we can translate it in a different way. And nothing showed up. Yes. So in actuality, that triangle array defined in that method had been deallocated, and that pointer reference, this GL trip pointer asks for a pointer reference. That pointer reference references memory that doesn't contain my triangle anymore. Great. So I can have the same geometry, and I can just use uniforms to translate it, or if I want to rotate it or scale it if I wanted. Do all sorts of things with that vertex shader. So that's all I got. There. Any questions? If not, if you have questions about your final projects individual to your situation, come ask me after class. Otherwise, I will see you all next week. Not next week, next Wednesday.